Good. So now that we've seen how pressure evolves with altitude, we're going to care about the equations in the altimeter. The altimeter is an instrument such as the one I'm showing you now on the screen that is going to give me some vertical position information. It's probably going to be an altitude or a height or whatever I want, as we're going to see. Good. This reasoning I'm going to follow now is only valid for the troposphere, but you can also try to do it for the stratosphere with the associated equations. For the troposphere, as we've seen, there is an evolution of pressure with altitude that is in accordance to this equation. And since this is a monotonically decreasing function, we've plotted it before, then we can get z as a function of p according to this equation. And this could be great if the atmosphere were always the standard, and it could be great if we were always interested in retrieving our vertical position with respect to sea level. But this is not always going to be the case, so we have to come up with a system that lets us have different vertical position solutions, being all of them obviously valid. So what we're going to do is we are not going to measure our vertical position with respect to sea level. We're going to measure our vertical position with respect to some reference surface or point where we know that there is a given reference static pressure. Good. So what we are going to do is we're going to retrieve deltas of z, being this the position where we truly are minus the position of the reference surface. And going through some algebra with this equation, you will easily retrieve this expression saying that this delta of z equals this term here on the right hand side. And this is the way altimeters are calibrated. If we input just the static pressure outside and a given reference pressure that we may choose, obviously associated to a given surface of reference, then we can get the vertical distance between the vehicle and that reference surface. It's important to note down here that the altimeter is going to be an instrument with calibrated values for all these sea level parameters, even for alpha. And the values that it's going to be calibrated with are, of course, international standard atmosphere values. So in this equation, when you are operating for the altimeter, you have to be aware that temperature at sea level means temperature at sea level in ISA conditions, and that alpha means alpha at ISA conditions. And of course, the constant of gases, the gravity, and all these parameters are constants that you should be familiar with and know. And the pressure would be obviously the pressure at sea level in ISA conditions when we are getting the readout from an altimeter. Okay, so depending on the reference pressure that we are introducing in our altimeter, given a static outside pressure, we will be getting a readout. This reference pressure is introduced in what we call the Boltzmann window. Here you have a couple of displays on two different altimeters, and you can easily read the Boltzmann window. This one here stating 30.14 inches of mercury, and this other one here also in inches of mercury. Be aware that normally we use millibar units, being the standard atmosphere 1013.2 millibars, but Americans use inches of mercury, and in those units it is 29.92 inches of mercury, the standard value, which is equal to 760 millimeters of mercury in a column. We're going to see now which are the three most typical reference pressures. First, we'll talk about Q and H. If you recall, we already anticipated a little bit what Q and H was in our METAR lesson. Q and H is nothing but the pressure that we would find if at a given point we drilled a hole and we reached sea level. So if we wanted to know what the QNH is over Pamplona, all we'd have to do is drill a hole, reach sea level, and there measure static pressure. That has nothing to do, this pressure here may have nothing to do with the pressure that we can find some kilometers away from that point. So let's say if this is Pamplona and here this is Alicante, the QNH is not the same, all right? If we select QNH on the Colsman window of an altimeter, we are going to read altitudes. Be aware that if Pref equals QNH, that means that Zref is equal to 0, and thus the readout of the altimeter is going to be altitudes. Good. We may also introduce QFE on the altimeter as Pref. QFE stands for the static pressure at a given point on the surface of the Earth, typically a runway threshold. So if the set of reference equals a given point, for instance, a threshold of a runway, then Pref equals QFE, and we are getting as a readout the height of the aircraft above this threshold. This is what we're gonna get as the readout of the altimeter. So we would be reading heights. If we use another thing named QNE as Pref, which is equal always to 1013.2 millibars, or what is the same, P at sea level in ISA conditions, or the standard pressure value, then we are going to get as a readout of the altimeter what we will name flight levels. And we're going to read, what we're reading on the altimeter is neither the altitude nor the height, it's just the vertical distance between the aircraft and an isobar of 1013.2 millibars, which depending on the day is going to be at a given point, fictitious, which might be interesting or not in most cases. We're going to see later what is the use of the QNE. Flight levels are defined as hundreds of feet. That means that if the vertical distance between this aircraft and this isobar of 1013 millibars is, let's say, 28,200 feet, we're going to name this as flight level 282. We are never going to call the last two zeros of this distance. So flight levels, remember, are always three numbers that express a vertical distance in hundreds of feet. Be aware that in the vicinity of an aerodrome, such as Granada, the one we are displaying here on this chart, all the obstacles are presented in terms of altitudes. Thus, the interesting thing when overflying this area at low altitudes or performing the approach is going to be to read altitudes on our altimeter, so we can compare our altitude with the elevation of these obstacles, thus knowing whether we can pass or overfly the obstacles or not. Good, so it's turned out pretty clear that in the vicinity of an aerodrome, it is more interesting to use QNH. But what can happen if, let's say, some aircraft departs from Madrid and in the middle of the flight crosses against another aircraft that departed from, let's say, Paris-Orly, and each of them is flying with respect to the reference of their origins. Well, since the QNH in Madrid is going to be different from the QNH in Paris-Orly, they are both going to be flying with respect to different references. And if we tried to space them, let's say with a vertical separation of 1,000 feet, let's assume this one is flying at 36,000 feet above sea level, or what he thinks is sea level, which is corresponding to the QNH of Madrid, and this other one is flying 35,000 feet above the QNH of Paris-Orly. This is not necessarily going to mean that here the vertical distance is going to be 1,000 feet, because these two references are different. Thus, what we are going to do is that aircraft during the cruise phase are going to fly using always the same reference, and that reference is of course the QNE. And we are not going to say that they are flying altitudes, they are going to be flying flight levels. So this one will be flying at flight level 360, and this other one will be flying at flight level 350, and thus we can assure that the vertical distance between these two flight levels, since they are using the same reference, is obviously 1,000 feet, and thus the operation is safe. So there is a moment in the operation when we have to change from QNH to QNE after takeoff. At which point are we doing that? Well, we are doing that when crossing an altitude named the transition altitude. The transition altitude is an altitude that is published on the standard instrument departure charts, or on some other charts, such as this one here. And when overflying it after takeoff, we change from QNH to QNE, we change from flying altitudes, or from reading altitudes to reading flight levels. Good. What is going to happen during descent? Well, during descent we will have to do the operation the other way around. During descent, we're going to find an aircraft that comes from its cruise phase flying flight levels using QNE as the PREF, and at a given point is going to set the local QNH on its Coltsman window, because he wants to read altitudes in order to perform a proper approach maneuver, knowing what his relative spacing is with respect to the obstacles near the aerodrome. So he's going to stop using he's going to stop flying flight levels, and he's going to start flying altitudes. This green line that I've painted here is named the transition level. And the spacing between the transition level and the transition altitude is what we will call the transition layer.